Welcome back. So this is the last lecture on memories. So this is like an extra lecture because we are not going in very details of memory. But without having this knowledge of memory, microprocessor systems design and interfacing is really not complete. It's not it. So this is sort of the concluding lecture, and probably we'll have some extra lectures if possible on some of the hands-on things to complete the entire chain. But officially this will be the last lecture. Okay, so let's actually delve into the memory aspects. So this is in fact a single snapshot of the entire course, I would say. So we started off with going very deep inside the CPU or the processor core, which is a arithmetic logic unit and registers. In our case, there is some interrupt controllers as well. So that's where we started off with. We started off with building our own 8-bit microcomputer so that you get a feel of the components of a processor core essentially works. Then we briefly abstracted it to the ARM Cortex M0 Plus core. I introduced you to the assembly language, which is very powerful. So that is one which is closer to the hardware, or in fact closest to the hardware. Or some people say closest to the hardware will be the binary opcode sort of system, right? But that's not difficult. I mean, that's not possible for us to code in that. So the one which is more human is assembly language. And then I also introduced you to write the things in C, and embed system, which is even more simpler in C. Okay, so that is on the software aspect, right? So that's what we discussed in detail, this part. Then we know that CPU or a microprocessor is sort of a software controlled system. It's a serial system, of course. So you have to write those softwares in assembly language or C. And then it is more of a load or store system, right? You have a memory, and from that memory, the codes which are written will be loaded into CPU, executed. Based on that execution, different actions will be happen. And bus is sort of peripheral bus or system advanced, we call advanced system buses. So whatever, advanced high performance bus or advanced peripheral bus, doesn't matter. Bus or set of wires, in this case, how many set of wires? Yes, 32 set of wires help you in moving the data from memory, from peripherals into registers, back to memory, and so on, right? So they are the essential nervous system in our computer system, right? In our CPU. And then we discussed, once we were comfortable with inside, we spent quite a lot of time in discussing on the inside part of the CPU and the assembly language part. Then we started looking outside. So we started with the simplest of the interface peripheral, which is actually the GPIOs, general purpose input output. And then we briefly discussed about interrupts and timers, their importance in computer systems. Unfortunately, by this time, in a normal scenario, you would have completed the lab sessions as well on these. But that is okay. Yeah, hopefully you'll be able to do that once you come back. Okay, so we'll wait for that. And then we discussed about the first serial communication, right? Serial communication is important because parallel is sort of impossible in modern day embedded systems because of the size constraint and power constraint. So typically we communicate with peripheral devices using serial communication protocol. And we discussed in detail individual sessions on UART, which is an asynchronous transmission protocol. Universal asynchronous receiver transmitter. Of course, it is a single line transmission or reception scheme, and some people call one-on-one or simplex scheme, correct? And then we discussed about the SPI protocol, which is a 4-wire or 4+ wire system. So one, it is a synchronous system, of course, so there is one dedicated clock line, then one data transmission, one for reception. So it is a duplex system, full duplex system. And then, of course, one for the chip select or the slave select, right? So that those are the 4 pins. So if you have multiple slaves, we have more slave select pins for wires. That means 4+ wire system, correct? And then last not but least, this is the most magnificent serial communication system, I would say, is the integrated circuit popularized by NXP or earlier Philips. So this is something like, again, a two-line system, one for clock, one for data. So it is definitely a synchronous system, and of course a simplex system, I would say, because one time it will only do read or write, and one wire, of course. The advantage here is there is an addressing scheme, 7-bit or 10-bit addressing scheme. That means you can connect 2 raised to 7 devices or 2 raised to 10 devices in the case of I2C. And that is the difference. So by now, I encourage you to definitely do hands-on, at least with Arduino system that you have at home. You should do that. And you should appreciate when and where to use these three. Okay, so by now it should be very clear as a system engineer what to choose for your next peripheral communication. Okay. Sorry. And then we discussed in the last class in detail about the analog world interfacing. I hope you enjoyed that lecture, and you will anyway touch upon these in future courses as well. Analog to digital conversion and digital to analog conversion. This is important because our world is analog, our brain is analog. So everything that we want to interface or tell the world or communicate to the world should be in the form of these devices. So they're universally there. A system without these is virtually impossible now. Okay. And now, last but not least, and probably the concluding one, is the hero of all these, because microprocessor without memory is, I don't want to compare that with, because it's something like something without brain, right? I mean, if you don't have anything without brain, it's completely useless. It's just a body, that's all, okay? So without memory, microprocessor has no meaning, and this is a lifeline, I would say. Some people say clock. Yes, clock is a lifeline, but this is the important aspect which is sort of unavoidable in a computer system. Okay? So let's go in a deep dive on the memory aspects. So this is the hierarchy of memory, not in terms of materials, but in terms of the speed of operation and the expense part. The capacity part. Okay. So I would like to put this is a beautiful chart in terms of pyramids. A lot of textbook has. So there's no one single reference. I borrowed it from many references, and would like to thank internet as well for this picture. So if you see here, I would say the bottommost is the magnetic tapes. Some people say it's outdated, but we'll discuss on that whether it's outdated or not. I have something to show you. So magnetic tapes, which started off in 1950s, I would say, or maybe much earlier than that, is still around and is the future, some people say, with the amount of big data that we're talking about, right? And then we have the hard drives. Nowadays, we have very fast hard drives, which is of solid state in nature, solid state drives. But we have the mechanical rotational hard drives as well, which is not outdated at all, the SATA ones, right? And then we have the ROM, which is typically, I would say, read-only in the sense, not the CD-ROMs, okay? So these ROMs are read-only in the sense, like while running, you cannot change it, but definitely programmable, as you can see over here, flash and electrically erasable programmable memories. So both are programmable, but once it is programmed, till the next programming is done, it is static, okay? You cannot change it. And we will have a discussion on what is the difference between flash and EEPROM, EEPROM in fact. Then we have our friend RAM, right? Two types of RAM is possible, static RAM and dynamic RAM. We'll discuss on those. Not really very detailed, but a very high level discussion on that. And without RAM, life is zero nowadays, right? Because higher the RAM, I'm not happy with even 128 GB of RAM in my system, because that's not enough. So higher the RAM, better is for you, because those are the short-term memories for you. Okay? So if you don't have short-term memory, everything is stored in a long-term memory, then you take a lot of time for executing anything, right? So that's why some people are very smart, because they have very good short-term memories, in the sense like immediately recollect something. Because I'm very poor in that, my RAM may be very poor, right? So that is the situation here. And then we have the cache memory, and cache is something like which is part of the CPU, I would say, not inside the core, just outside the core, but much better than the RAM. Okay, so we'll discuss on that. There is something like L2, L1, L2, L3 in terms of hierarchy, and these are made of static RAMs typically. So we'll discuss on these as well as we go on the slides. And then topmost is our friend, very few in number, which are the registers, which are actually embedded inside the core. So they are the only memory which is there right there in the CPU, and is have direct access to the CPU, right? Direct connectivity to the CPU. So that's something like the secretary to a big minister, right? He has direct access, and if you want to communicate to minister, you have to go through the secretary. There is no bypass, right? So that's the kind of thing. So from top to bottom, I would say it is very cheap, and number of bytes that you can afford is much more. From bottom to top, it is very few in numbers, very expensive, and of course, in connection with CPU or the execution part, it's the fastest, right? If you store something in register, a program will be very fast, right? That's the concept. Okay, now let's take each one of them individually and try to understand in some detail, okay? Before going there, just a refresher of our KL25 is a memory map. We already had a deep discussion on this. I don't want to spend it again. So again, I just want to highlight that this entire system is a mix of all these types of memories, right? So that is very important to remember, okay? So we have in our system around 128 KB flash, and that is why the name KL25 is at M128, if you remember. We choose the board, right? So that's a reason. And around 16 KB of SRAM is there for us, okay? This is a sample case I'm saying, okay? So many types of SRAM is there, so many hierarchy of SRAM is there to cover 512 MB. Similarly, flash also to cover the 512 MB, but each individual piece is something like 128 KB. Okay? So now registers, we already saw this sort of layout for our Cortex M0 Plus. So many general purpose registers, and then program counter, link counter, and stack pointer. Some special status registers over here. So all these registers have direct connectivity to the CPU. So this is an illustrative figure. So we have the core here, the ALU here, and each of these registers are directly connected to the ALU. Okay, so this is your bus, for example. So this bus will come to the register, and register will convey that data to the ALU. The result will also get stored in register, and from register it goes to the bus and to the memory, right? So that is the typical path. So you can think of individual, there is a hardware digital circuit which is inside, which connects the registers individually to the ALU through some mux arrangement, something like this, a multiplexer arrangement like this. So this is important to have in your mind. They are very few in number. You just cannot add registers on and on, because then that increases the complexity of your core. You can't afford that, right? So very few registers in number. And modern day registers typically have around 12 to 13 general purpose registers inside the core. That is even high-end machines I'm talking about. Okay, so that is a general trend. Moving on, so we have the cache memory. So basically, for example, we have a single core system, I would say. So there is an ALU plus control unit here. Just outside is the registers. They have direct connectivity to the ALU, something like input and output also to the register. Then there is a bus system which is outside, which is coming, and typically it goes to the registers and then to the ALU. But nowadays, modern day machines, later they realized that you cannot keep on adding the register number. Instead, I would add something known as SRAM into that, and they named it as L1 cache, level 1 cache. So it is something like a small memory which is inside the CPU core, something like in the range of 2 KB to 64 KB. High-end systems are around 64 KB. And this is right inside the core, but it is not registered, no direct connectivity with the ALU. But it is much closer because there is no bus involved, no need of putting everything from memory to the bus to the register to the ALU. Here it is inside the cache. So typically you can store some small amount of data in the cache. So before starting any program, so that the program can be executed much faster. So if next time you hear about a core having L1 cache memory of this, always remember this, okay? So it is that RAM which is direct, almost there with the core, not direct connectivity, but the connectivity through the register, there's no bus involved, so that is important. So that, if you have higher cache memory, better for you, right? So that is how typically, these numbers are for embedded systems. Of course, if you have a server system, it may vary, it may be in MB, okay? If you see something like Intel, these Xeon processors and all, right? They may have even memory in terms something like 8 MB of cache memory. Okay, so that is different. Here I'm talking about generally. Okay, generally this is the amount of memory which is there for the L1 cache. Okay, and then in hierarchy, slightly outside of it, you have the L2 cache, which is again higher in memory size. And then you have the L3 cache, which is in NB. Okay. So this is in the order. So I would say the distance away from the ALU. Okay. So this is level 1, level 2, level 3. And then you have the RAM system. And then you have outside is a bus. And then you have the ROM or whatever memory is outside, right? So this is the order in which even your laptops or desktops or workstations work. So you have registers which are right there directly connected with the ALU. The next best is L1, level 1 cache. Next is L2, next is L3, and next is actually the RAM. And then so on, the hierarchy goes on. And if it's a double core system, for example, nowadays we have multi-core systems, so many cores, like for example, 6 cores is typically there in most of the systems. So they are actually arranged something like this. So each core will have a level 1 cache. So always remember that, okay? So there is a level 1 cache associated with this core, and there is another level 1 cache associated with this core. So that is the complexity of a computer system that you're dealing with nowadays, okay? So think about controlling such a system. It's so difficult, but then there's a hierarchy, the APIs are there for you so that life is much easier for you. So crisply, if I want to put it this way, so if registers are not affordable for you, the next best friend is the cache memory, and even 3 levels of cache memory exist in the case of a computer system or a microprocessor system. Going forward, in the order, we started with the registers, then with the cache memory, now with the RAM. Okay, so RAM, 2 types are there, static RAM and dynamic RAM. And this is how it looks like. A typical static RAM cell, a 1-bit cell, is looking like this. And for a dynamic RAM, it looks like this. So the major change I would say is here you have a passive component of capacitance. Okay. In the case of a DRAM compared to an SRAM, where it is all MOSFETs, I would say. If you studied MOSFETs, you may understand this circuit. Otherwise, just ignore it. You will study at some point of time solid state devices, for example. That time you will understand these concepts. You may have to come back and read it. Okay, so this is a bit line and this is a complementary bit line, and similarly here there is only 1 bit line, and this nicely represents that there is a complement and original and complement sort of thing here. So 1 and 0 is represented here, and here 1 and 0 is represented by full charge, no charge of this capacitance. So if you see the advantages of static RAM, it is fast and there is no refreshing required. Here it is, the advantage I would say is density is high because you can pack, the number of components is less, so you can pack a lot of them. Less area is occupied for 1 bit, so many bits can be packed quite easily, and it is less expensive. Now let's see why this is fast and why no refreshing is required here. Because a capacitance component is, you can see over here, that requires some amount of time to charge, right? So there is a charging time involved, so it is obviously slow. And here there is no capacitance component directly, so that means this is faster, okay? And this is slower. And here you need regular refreshing because capacitance may get discharged as it stays over time. So if you don't refresh, it will get dissipated, or it will, I would say, get not dissipated. It will have 0 charge in no time, and you need regular refreshing. Okay, so that is the thing. And disadvantage is just the opposite of this large silicon area, because you see, imagine for 1 bit it takes so many components. So imagine a 32-bit, it takes so many components, right? It's expensive. Okay, and here dynamic RAM is slow, right, because of the capacitance presence, and again it requires regular refreshing. So where is it used? Static RAM typically used in cache, okay, cache memory, and the main RAM is typically dynamic RAM. And that obviously you can understand that because main RAM requires a lot of memory, and that means you need to have something which goes for high density. And main RAM can be slower than cache, so obviously you can go for dynamic RAM. So next time somebody asks you what type of memory is cache, immediately it should come to your mind that it is static RAM. And remember, there is no capacitance component in that. Okay? So that is the helping point for you. Dynamic RAM, typically all the main RAM that you have is all dynamic RAM. Going forward, one more thing. Actually, there are many interesting technologies of replacing capacitance with resistance. Resistive RAM, in fact, one of our PhD student in electrical engineering is doing his PhD work in resistive RAM. So moving on, ROM, read-only memory. As I said, it is not the CD-ROM concept. This is what mostly for the data read operation, for example, or I would say the code memory option. So two types are possible: flash memory and EEPROM, electrically erasable PROM. So EEPROM is typically based on NOR, and flash memory is typically based on NAND. If we go back and see the structure of NAND and NOR, maybe the first lecture in our microprocessor design, you should be able to see the advantages and disadvantages between these two. Okay, and then if you see the advantages in terms of number of reads and writes, this is more for more reads, and this is equally true for both read and write. This is more expensive, this is less expensive, and that is obviously flash memory is very popular. Okay? Read time, this is much faster, this is slower. Okay? Programming, this is more time, this is less time. That is why flash memory is gaining popularity. Voltage, this is less, this is more, obviously, then power will also be higher for flash memory. Erasing time, I have a beautiful slide on the next one, which actually shows erasing difference between EEPROM and flash memory. Because this one is erased byte by byte, so it takes a lot of time. This is erased as a block or a wall. You can actually sweep it as a wall, okay? So that is it. Data size, typically EEPROMs are small and these are large. This is a very high level overview because if you want to learn specifically on flash and EEPROM, you may have to take a course on advanced memories. Okay, so that is something for specialization for higher studies. Okay, but if I'm able to motivate you in that direction, that is job half done for me. Okay, and this is that chart. This is really attractive for me because this really highlights the difference between EEPROM and flash. And sometimes pictorial representations are much more easy for you. Right? So this is how it looks like. So EEPROM, as I said, it erases byte by byte. So it is something like you have a what do you call duster in your hand and you're cleaning the board. It takes so much time. So if we had something like this arrangement, smart, right? You can clear it as a block or a wall. Okay, so that is the main difference. Now, coming back, so we started off with registers, cache, RAM, ROM, now hard drives. Okay, so this might be the most common, maybe most common for you. I mean, the sense like hearing, right? You might have heard about SSDs and hard disk drives. And if nobody has seen inside, how does a typical SATA drive, SATA drive, or the popular hard disk drive that you have it? It is something like this. There is a motor here and there is a spinning wheel, and basically wherever this is pointing, that sector is being read. Okay, the data is being read. That is why this is slow. This is mechanical, so it takes some time for this to move from here to here. So wherever it is, that sector data will be read. Okay, so we have to change it, and that takes a lot of time, and that is why it is slower than it's something like a solid state device, which is something like this. There is no rotational moment there. It will be all a series of NAND flash memories, which we discussed here. Okay, these flash memories, so many of them arranged together with a microcontroller, which is so this is something like this. I would say nowadays the modern trend is like to put a microcontroller into an SSD. Okay, if you are not seeing that, that is the future, and that will revolutionize a lot of things, including the analog computing. Okay, something like all computing is digital nowadays. There is a trend towards analog computing because brain does analog computing. So something like instead of having a microcontroller cache memory surrounded by SSDs hard disk, why don't you put microcontrollers into the SSDs and hard disks? That will be amazing, because then that bottleneck between memory to bus to CPU is gone, right? So that is what the future trend is. Somebody is very interested, I definitely encourage you to take a higher degree in this, because this is something which is very, very, very interesting. So instead of rotational mechanical component, you have the electronic component here, and that is why SSDs are so popular, and that is why SSDs are very expensive. Okay, so you can imagine that. And last but not the least, magnetic tapes. Okay, so this is the old picture, 1952, introduction of commercial computer tape storage by IBM. So IBM has been the pioneer or forefront in terms of magnetic tape memory. So this is really sort of analog tape, and then they introduced the digital tape also, which is something which is similar to hard disk, I would say. This is a cartridge which disappeared at some point of time, but I would like to put you this article, which is listed down here, which is in 2018 it was there. I would like to just quickly highlight that article for you. So why the future of data storage is still magnetic tape. This is very, very important. Okay, and highly encourage you to read it up. This is 28th August 2018 Spectrum. If you have not read this, please go ahead and read this. Data disk drives are reaching their limits, but magnetic tapes just get better and better. Okay, so life is still very, very happy here. Okay, so please read it. It's a very beautiful read for you, introducing a lot of history into it, and then where is the future. So highly encourage you to take it up. This is the modern day data storage from IBM, if you want to see that. So please have a look at it. Okay? So coming back, so we completed it, and I just want to introduce you to something which is very, very important, and which is the modern day memory access for many systems. And this is something known as direct memory access, DMA. You might have seen this or heard this term many, many places. Okay, so just to make highlight, I mean, what is the importance of it? I'm not going in very detail because that is beyond the scope of our course. But I just thought it is important that you have to understand this as well, okay, to appreciate the beauty of modern day systems. So CPU, as you know, it's already there, and then you have memory here. So through the bus, you whatever data you want to read. Okay, so let's say I just want to take an example which is very, very easy for you to understand. You are putting a portable flash drive, USB drive into your laptop or desktop, and then you want to copy a set of files from that to your local drive. Okay, so that is the task that you are going to do. So basically, you are putting in your flash drive, and then you select the files, and then you drag it to your local C or D drive, right? So very often you do that. And then immediately a window pops up in front of you saying that you are having the transfer, okay? So now imagine that it is done in a very trivial way, direct way. Then how it happens? So you put the USB drive here into the input peripheral. It can be USB or whatever. So you put it there, and then you copy, the window opens, you copy that. So it takes some amount of time. For that data, it goes to the CPU through the bus, and from CPU, it goes to the memory location, which is your C or D drive. So one cycle for basically transferring the data from your peripheral device into the CPU through the bus, and another cycle for that data to be stored in the memory. So CPU issues a load command to load the data from your peripheral into its internal memory, and then store command to store it into the memory that you have. And this requires one cycle. Imagine that you have GBs of data. It takes so much time. It's not good to actually have everything through the CPU, right? Because CPU get hang. It will not do what it is supposed to do. You may be running some program on the CPU, it will get hang. So it's not the way to go about. So instead of that, if you have something like CPU is the controller, but then there is a direct memory transfer between your input, output, peripheral to your memory. So something like direct data transfer from your flash drive to your local C or D drive. That is what this means, direct memory access means. So CPU is sort of a facilitator here. Data is not gone through its bus system. It is not coming to the CPU core, but it will control the entire process, and then data will be transferred from the peripheral to the memory. Okay, so let's see how it happens. In this very high level picture, so don't get worried about this, but just for your understanding. So you have the CPU core here, all our programs are running here. You have the bus and the interrupt system, which is shown over here, okay? And basically there is interrupt based control from CPU to, there is something known as a DMA controller, which controls the entire process. Something like our NVIC controller or the port controller, GPIO controller or SPI controller, whatever controller. DMA also has a set of registers or controller associated with it. Okay, and then there is a memory, of course, which is our local drive or the whatever disk drive that you have. Okay, and then there is a peripheral controller. In this case, this can be a USB controller, and then you put a USB drive into this. Okay, So data from that USB drive actually comes and fills in the buffer, which is an internal memory to this peripheral controller. Okay, and that is very important to notice. And then DMA controller typically has an address location register, which has the address of the memory to which you want to write the data from your peripheral device. Okay, can be a flash drive, for example, and number of bytes you want to transfer. So there is a register to store that number of bytes also. And then there is control register, which will issue the control signals so that the entire process happens without involvement of CPU. So let's do it. So before that, I would like to connect a USB drive. So this is a USB flash drive. Your flash drive is here, correct? So that flash drive is plugged into your peripheral controller. Let's assume this is USB. Okay, so this is the USB, and you have a buffer. So the data, and then you connected it, and then what you do is you copy a set of files, right? And then copy that your memory in physical way, virtually. A GUI opens and you drag it to the local drive. The moment you do that, it goes and triggers an interrupt to the CPU saying that, okay, CPU, please transfer this file. Okay. The first step that CPU does is it will request the DMA controller to take the charge, and DMA control will allocate the address, will find out where you want to transfer your data. So that address will come and sit here. How much of data you want to transfer, that estimate will come and sit here. And what sort of control signals that you need to. If it's a read operation, it's a write operation. That also will come and sit here. The moment the request is done, CPU will be relieved from its job. It can do whatever it was doing. It will go and execute some programs, for example. And then DMA controller will take charge. So the first step then from DMA controller side is it will issue a transfer request. Okay. So DMA controller issues a transfer request. And then what happens is data will get transferred from your USB drive and comes and sit in your buffer. Okay. Once this buffer is full, it will be the DMA controller will be issuing a data transfer from your buffer to your memory location. Okay. And then once this data transfer is done and the buffer is empty, the entire data is transferred to the memory, buffer becomes empty, an acknowledgement will be sent back to the DMA controller. Okay. And DMA controller will check if the byte count is 0. Okay. Byte count is reduced. Is it 0? If it is not 0, the steps are repeated. So again, it will have a transfer request. Data is again coming. Buffer is transferred. Buffer empties. Acknowledgement comes. The moment the byte count becomes 0, that means your data transfer is over. Okay, everything is done. And that stage, the DMA controller will issue an interrupt to the CPU saying that, okay, the data transfer is done. Everything is done. Please go ahead and issue a command to your user saying that, okay, data transfer is complete. And that is where you will see that in the screen that the data transfer is complete. Okay. This is how the entire data transfer happens when you plug in a USB drive and then transfer the data to your CPU. Interesting, is not it? So our Freedom board also has a DMA controller built in. I'll just okay, just show you that. So go back to your Bible, the document manual, you see chapter 23 and chapter 22 will deal about the DMA mux and DMA module. Those who are interested, please have a look at it. These are the address. SAR is the source address register. DAR is the destination address register. Source address register will be the address of your USB drive, for example. Destination address register will be the address of the hard disk. And this is a data status register. Then that is what the buffer acknowledgement will come from. BCR is byte count register. Okay. And then DCR is, just go back and see, is the control register. Okay. So that is. And then this is entire system. Those who are interested, actually the best way to learn this level is actually to go and program for yourself. You will find a lot of codes in Embed or a lot of codes in even in KL25Z, Keel Microvision codes. If you search for DMA, you will get a lot of bare metal codes. Those are very easy to understand, and I should say the best way to learn at this low level, which I can't do everything in class, is to make sure you do it and you understand it. And if you are stuck somewhere, I'll be more than happy to help you out. Okay, so I think that completes the entire lecture series. And we started off with 8-bit microcomputer. Hope you enjoyed that. You did yourself build that 8-bit microcomputer using basically the logic gates, I would say, or even small components. Then we discussed about ARM Cortex M0 Plus in detail, the architecture of it. Then we discussed about assembly programming language, correct? That's what we discussed about. Then we discussed about uh, the peripherals, starting with GPIOs, interrupts, timers, serial communications, ADC, DAC, and then in this class, a very high level description on the memory. Hope you enjoyed the journey. And as I said at the start of the lecture, if I'm able to motivate at least one of you to take higher studies in this, to take a job in this, I'd be more than happy. And please do give all your feedback, all your questions, all your doubts, all your suggestions in the discussion forum. I'd be more than happy to implement that in the going forward courses. And I hope you enjoyed. I had a good time with all of you. And unfortunately, we had to end the physical interaction between us. But that never stops. Feel free to email me. Feel free to come and discuss with me in future as well. And we will have a live session. Hope everyone will join for that. Until then, let's wind up. And thanks for joining.